Welcome back, everyone.
It's great to be here.
Today, we're taking a deep dive into a topic that's really like the bedrock of so much of the world around us.
Yeah, you can't really stape it.
We're talking about mensuration.
It's one of those things that kind of underpins everything.
You've sent in an amazing collection of resources, actually covering perimeter area, all those 2D shapes like polygons, and then surface area and volume, getting into the 3D world of solids.
Cuboid cylinders.
Yeah, all the classics.
Exactly. And our mission today really is to distill, to pull out the essence of how these measurements work.
Right, because it can get really detailed, and we want to,
Yeah, we want to make sure that we come away with a solid understanding of the core concepts.
the why behind the what.
Exactly.
So let's kick things off with something that maybe doesn't seem that exciting at first,
Okay.
but really gets interesting the more you dig into it.
I like where this is going.
The area of polygons.
All right.
Now, I know we've all seen squares and rectangles,
The base.
but when you start looking at shapes like pentagons,
Things get a little more interesting.
they do. And your sources actually do a fantastic job of illustrating this.
Oh, good.
In figures 9.1 and 9.2.
Okay.
And what they show is how you can break down these more complex shapes into simpler ones.
Yeah, that's a classic strategy in geometry.
Right, using like diagonals to create triangles, or even perpendicular lines to make a mix of triangles and a trapezium.
And that's where the real magic happens. Because suddenly you're not dealing with a weird shape.
Right.
You're dealing with familiar territory.
Yeah, you're working with shapes that we already know how to find the area of.
Exactly. And by breaking down the complex into the simple, you can actually apply those familiar formulas and figure out the area of something that initially seemed quite challenging.
So it's all about using what you know to figure out what you don't know.
Exactly. Problem solving at its best.
Now, the Try These section in your materials really dives into this.
Okay, let's see it in action.
With this polygon, ABCDE, in figure 9.4,
All right, A, B, C, D, E.
they've broken it down into a triangle, AFB, a trapezium FBCH, and then two more triangles, CHD and ADE.
Okay, so they've really gone for it with the dissection here.
And the best part, they've given us all the dimensions.
Oh, that's helpful.
So AD is 8 centimeters, AH is 6 centimeters, AG is 4 centimeters, AF is 3 centimeters.
Okay, keeping track.
And then the perpendicular is BF at 2 centimeters CH, at 3 centimeters EG, at 2.5 centimeters.
That's right, so we've got all our measurements laid out.
And what they do is walk you through step by step how to calculate the area of each of those smaller parts.
So it's like a recipe?
It is.
For finding the area?
Right. So for triangle AFD, for example, it's just half the base times the height, AF times BF.
It's a pun familiar.
Exactly.
Yeah.
For the trapezium FBCH, they use that formula with the sum of the parallel sides, BF and CH, multiplied by the height, FH.
And they even show you how to find FH by subtracting AF from AH.
It's all right there.
Very convenient.
And then the other triangles, they follow that same basic area formula.
Half base times height.
And then the grand finale.
What's the big reveal?
You add up all those individual areas, and you've got the total area of the polygon.
So satisfying when it all comes together.
I know, it's like solving a puzzle.
Yeah, it really is.
Now, speaking of shapes that we can break down,
What do we have next?
let's talk trapeziums.
All right, bring on the trapezium.
Example 1 sets the scene for us.
Lay it on me.
Imagine a field
Okay.
that's got an area of 480 square meters,
All right, a decent-sized field.
a height of 15 meters, and one of its parallel sides is 20 meters long.
Okay, so we've got one side in the height, but we're missing the other parallel side.
Exactly. That's the challenge.
So how do we tackle this?
Well, this is where the area formula for a trapezium comes in handy.
Area equals 1/2 h times a plus b.
Now we know the area.
480 square meters.
A height, 15 meters, and one of the parallel sides, let's call it a chine, is 20 meters.
So you've got 3 out of the 4 variables.
Plug those values into the formula and bam.
We're left with an equation where b, that missing parallel side, is the only unknown.
And with a little bit of algebraic maneuvering,
Right, a little bit of solving.
you find that b is 44 meters.
There it is.
So it's really cool how we can use a formula like this to find a missing dimension.
Yeah, when we know other properties of the shape.
And this applies to all sorts of real-world situations, too.
Oh, absolutely.
Like if you're trying to figure out the dimensions of a piece of land.
Or maybe designing a building.
Exactly.
Geometry in action.
All right, ready for another four-sided friend?
Hit me with it.
This time it's the rhombus.
Okay, I like the rhombus. It's got a certain elegance to it.
It does?
So what's the situation with this rhombus?
Example 2 tells us we've got a rhombus with an area of 240 square centimeters,
Okay.
and one of its diagonals is 16 centimeters long.
All right, so we need to find the length of the other diagonal.
Exactly. And this is where knowing a little something about the properties of a rhombus helps.
Always good to have those in your back pocket.
Because the area of a rhombus can also be calculated using its diagonals.
Area equals 1/2 d1 times d2.
And since we know the area, 240 square centimeters, and one diagonal D1, 16 centimeters,
We're in business.
we can just plug those values into the formula and solve for the other diagonal D2,
Which turns out to be,
50 centimeters.
that's a nice round number.
It is, and I think it's interesting how the area of a shape can be related to different sets of its dimensions.
Yeah, like we saw with the trapezium and now with the rhombus.
Right, so you've got these different ways of approaching the same problem.
Multiple paths to the solution.
Okay, ready to level up to a six-sided figure.
All right, let's do it.
You know,
I'm intrigued.
we're talking hexagons now.
The hexagon
So-
is shaped with a lot of personality.
It does.
So what's our hexagonal challenge?
Example 3 presents us with a hexagon with each side measuring 5 centimeters.
Okay, equal sides a regular hexagon.
Exactly. And what I love about this example is that your sources actually show two different methods
Oh, cool. 2 for the price of 1.
to calculate the area courtesy of Aman and Ratima.
A collaborative effort.
Figures 9.7 and 9.9.
Got it.
Okay, so let's start with Aman's approach.
All right, Aman, lead the way.
Aman takes this hexagon, an OPQRM, and divides it into two identical trapeziums
Okay, so splitting it down the middle.
by drawing the diagonal in Q.
All right, so now we've got those familiar trapeziums.
And because it's a regular hexagon, we can use that symmetry to our advantage.
How so?
Well, we can determine that the parallel sides of each trapezium are 11 centimeters and 5 centimeters.
Okay,
And the height is 4 centimeters.
got it. So we have all the dimensions we need
We do.
to apply the trapezium area formula.
Exactly. So 11 plus 5 times 4 divided by 2.
That gives us 32 square centimeters for one trapezium.
But remember, we've got two of them,
Ah, right, so we double it.
and we get a total area for the hexagon of 64 square centimeters.
Okay, so Aman's method is all about those trapezium.
Now, Radima takes a different route.
All right, let's see what Ridima's got.
She splits the same hexagon into two congruent triangles, MNO and RPQ,
Triangles this time.
and a rectangle MOPR.
So a different kind of dissection.
Right. And she calculates the base of those triangles to be 8 centimeters
Okay.
and the altitude to be 3 centimeters.
All right, so we can find the area of the triangles.
1/2 times 8 times 3 equals 12 square centimeters for each triangle.
Got it.
Now, the rectangle in the middle has a length of 8 centimeters and a width equal to the side of the hexagon, 5 centimeters.
So its area is 8 times 5 equals 40 square centimeters.
And just like before we add those all up,
12 plus 40.
and we arrive at the same total area of 64 square centimeters.
That's really neat.
It is right.
Two completely different approaches, and they both lead to the same answer.
It's like there's no one right way to solve these problems.
Exactly. It's all about finding the method that works for you.
As long as your logic is sound and your calculations are correct.
You'll get there.
Okay. Ready to step into the third dimension?
All right, let's get 3D.
We're moving from those flat, two-dimensional shapes to the world of solids.
Cubes, cuboid cylinders.
And here we start talking about surface area.
So now we're considering the total area of all the surfaces of a solid.
And your sources are so helpful because they include these nets
Oh, those are great for visualizing.
in figures 9.16 and 9.20.
Yeah, it's like unfolding the shape.
And it shows you what the 3D shape would look like if you laid it all out flat.
It really helps to see how all the individual faces contribute to that total surface area.
Let's start with the cuboid.
All right, the rectangular box.
6 rectangular faces.
And the total surface area is just the sum of the areas of all those faces.
Right, and since opposite faces are identical, it simplifies to that formula,
2 times pound plus BH plus HL.
where L is the length, B is the breadth, and H is the height.
Got it. Length, breadth, height.
And they give us a handy example,
Okay, let's work through it.
where L is 15 centimeters, B is 10 centimeters, and H is 20 centimeters.
All right, so we just plug those values into the formula.
And we get a total surface area of...
1,300 square centimeters.
Now, what if we're only interested in the sides of the shape?
Ah, like if you were wrapping a present.
Exactly.
And you only wanted to cover the sides, not the top or bottom.
That's where lateral surface area comes in.
It's all about those side faces.
And for a cuboid, it's calculated as 2H times L plus B.
So we're essentially finding the area of those 4 side rectangles.
And this has real-world applications, too,
Oh, tons of them.
like painting a room.
Yeah, you usually don't paint the floor or the ceiling.
Just those walls.
So lateral surface area is what you need to know.
Now let's simplify things a bit.
Okay, I'm all for simplicity.
Let's talk cubes.
All right, the perfectly symmetrical cuboid.
All sides are equal.
So finding the total surface area of a cube with a side length L,
It's pretty straightforward.
it is, because you've got 6 identical square faces, each with an area of L squared.
Mm-hmm.
So the total surface area is simply 6L squared.
Nice and clean.
Elegant and efficient.
All right, ready to tackle a cylinder.
Bring it on. I think
Okay.
I'm ready for the round challenge.
Your source, make sure to specify that we're dealing with right circular cylinders,
Okay, so those nice straight up and down cylinders.
like the one shown in figure 9.12.
Got it. The classic cylinder.
So how do we approach the surface area of this round friend?
Well, a cylinder has those 2 circular bases
Mm-hmm.
and that curved surface connecting them.
Right.
Now, the lateral or curved surface area, you can kind of visualize it as if you unwrap that curved part.
Oh, like peeling off a label.
Exactly. And it forms a rectangle
Okay.
where one side is the height of the cylinder H
Mm-hmm.
and the other side is the circumference of that circular base, 2 pi r.
So the lateral surface area of a cylinder is 2 pi rh.
2 pi r h.
But of course, we need to add in the areas of those 2 circular bases to get the total surface area.
Right, we can't forget about those.
Each circular base has an area of pi r squared,
So we add 2 of those to our lateral surface area.
and we get the total surface area of a cylinder.
2 pi r h plus 2 pi r squared.
And they actually give us a nice factored form as well.
Oh, even better.
2 pi r times r plus h's.
So much easier to work with.
Now let's see these surface area formulas in action with some real-world examples.
All right, let's get practical.
Example 4 takes us to the world of aquariums.
Oh, I love aquariums.
It's a cuboid shape,
Okay.
but there's a twist. We only need to cover the base, one side face, the other side face, and the back face with colored paper.
So we're not covering the entire cuboid?
Nope, just those specific faces.
Interesting.
The external dimensions are 80 centimeters by 30 centimeters by 40 centimeters.
All right, so we've got length, width, and height.
So to figure out how much paper we need to calculate the area of each of those faces separately.
So it's like a selective surface area problem?
Exactly. So first, the
Yeah.
base length times width, 80 times 30.
That's 2,400 square centimeters.
Then one side, face width times height, 30 times 40.
1,200 square centimeters.
The other side face is the same.
Another 1,200.
And finally, the back face length times height, 80 times 40.
That's 3,200 square centimeters.
That does all up.
2,400 plus 1,200 plus 1,200 plus 3,200.
And we get a grand total of 8,000 square centimeters of paper needed.
Okay, so we really had to break it down.
But it shows how you can apply surface area to specific parts of a shape.
Based on what you actually need to cover.
Right, not always the whole thing.
Makes sense.
Okay, ready for some interior decorating?
Oh, I love a good decorating project.
Example 5 is all about whitewashing a room.
Okay.
We've got a cuboidal room with internal dimensions of 12 meters by 8 meters by 4 meters.
All right, a good-sized room.
And we need to figure out the cost of whitewashing the 4 walls at rupees 5 per square meter.
Okay, so we're looking at the lateral surface area.
You got it.
And then we'll see how much more it would cost if we include the ceiling.
So first things first, those 4 walls.
2H times L plus B.
2 times 4 times 12 plus 8.
That gives us 160 square meters.
Multiply that by the cost per square meter, rupees 5.
And that comes out to rupees 800.
Now let's add the ceiling to the mix.
All right, so we need the area of the ceiling.
Length times breadth, 12 times 8,
96 square meters.
times rupees 5 per square meter.
Rupees 480.
So if we add the cost of the walls and the ceiling,
800 plus 480.
we get a total cost of rupees 1,280.
So we can see how both lateral and total surface area come into play in a practical situation like this.
Right. You might choose to only paint the walls.
Or you might go for the full ceiling treatment.
And knowing these surface area formulas.
Helps you figure out the cost in advance.
Okay, ready for some architecture?
Always?
Example 6 features those grand cylindrical pillars that you often see in buildings.
Oh yeah, they add a certain something.
They do.
So what's the pillar situation?
We got 24 of these pillars, each with a radius of 28 centimeters,
All right.
or 0.28 meters,
Got it.
and a height of 4 meters.
They sound impressive.
And the task is to find the total cost of painting their curved surfaces.
So just the lateral surface area?
Exactly, at rupees 8 per square meter.
Okay, so we need that 2 pi RH formula.
You get, so 2 times 22/7 times 0.2, 8 times 4.
That gives us 7.04 square meters for one pillar.
But remember, we have 24 pillars.
Oh, right. So we multiply that by 24.
And we get a total curved surface area of 168.96 square meters.
Times rupees 8 per square meter.
Gives us a grand total painting cost of.
Rupees 1,351.68.
So those surface area formulas are pretty handy for contractors.
Yeah, absolutely. They need to know how much paint to buy.
Yeah, how much to charge for the job.
It all comes down to surface area.
Okay, time for a little twist.
I like twist.
Example 7 gives us the total surface area of a cylinder, 968 square centimeters,
Okay.
and its radius 7 centimeters.
But this time we need to find the height.
Exactly, so we have to use our knowledge of the formula
2 pi r times r plus h.
and work backwards.
A little bit of algebra.
Plug in the values for the total surface area and the radius, and solve for h.
It's like solving a mystery.
It is. And after a bit of mathematical manipulation,
We uncover the height.
15 centimeters.
There it is.
Okay, we've explored area and surface area quite a bit.
I feel like we've covered a lot of ground.
Now let's dive into volume.
Okay, let's get into the space within.
It's all about how much space a three-dimensional object takes up.
Right, like how much you can fit inside something.
And your source reminds us that we use those cubic units
Like centimeters cubed, meters cubed.
to express volume,
It makes sense, right? Because we're dealing with 3 dimensions.
length, width, and height.
So our units need to reflect that.
And the first solid they explore for volume is the trusty cuboid.
The good old rectangular box.
And they even suggest a fun little activity with 36 cubes to help visualize this.
Oh, that sounds interesting.
I think it's on pages 115 and 116.
Okay, I'll have to check it out.
And the idea is you build different cuboids using those same 36 cubes.
So you're experimenting with different arrangements.
Exactly. And what you start to notice is a pattern.
Okay, tell me more.
No matter how you arrange those 36 cubes, the product of the length, the breadth, and the height will always be 36.
Ah, so there's this inherent relationship between the dimensions and the volume.
And that leads us to the formula for the volume of a cuboid.
Volume equals L times B times H.
Or, another way to think about it is,
The area of the base times the height.
which makes sense.
Right, it's like stacking up layers of the base.
So let's build up the volume.
Exactly.
Now, if we simplify things a bit and make all the sides equal,
We're back to the cube.
we are with a side length of L.
So now L equals B equals H.
And the volume formula becomes even more concise.
Volume equals L times L times L, which is just L cubed.
So simple, yet so powerful.
It really captures the essence of a cube.
Okay, ready for the cylinder volume challenge?
Hit me with it.
Does that same principle of base area times height apply here?
Well, let's see. A cylinder has that circular base with an area of pi r squared.
And then that circular shape extends along the height
So it's like stacking up those circular layers.
to build up the volume.
It's
The volume of a cylinder is
Pi r squared h.
base area times height.
It's a beautiful consistency across these shapes.
Now, your source also briefly touches on the connection between volume and capacity.
Oh, yeah. Those
Okay.
terms get used a lot, especially with liquids.
And it's good to remember those key conversions.
1 milliliter is equal to 1 cubic centimeter.
1 liter equals 1,000 cubic centimeters.
And 1 cubic meter is a whopping 1,000 liters.
So if you're ever dealing with liquids or containers.
Those conversions will come in handy.
Okay, let's put this volume knowledge to the test with some more examples.
All right, I'm right.
Example 8 throws us a cuboid with a volume of 275 cubic centimeters
Okay.
and a base area of 25 square centimeters.
So we need to find the height.
And this is where that rearranged volume formula comes in handy.
Height equals volume divided by base area.
So 275 cubic centimeters divided by 25 square centimeters.
Gives us a height of 11 centimeters.
It's like working backwards from what we know.
Exactly. Detective work in the world of geometry.
Okay, example 9 takes us into the world of warehousing.
Logistics, here we come.
We've got a go-down shaped like a cuboid,
Okay.
60 meters by 40 meters by 30 meters.
A massive space.
And we need to figure out how many smaller cuboidal boxes,
Okay.
each with a volume of 0.8 cubic meters, can fit inside.
So it's a packing problem.
It is.
We need to find the go-down's total volume first.
60 times 40 times 30.
That's 72,000 cubic meters.
And then we just divide that by the volume of one box.
72,000 divided by 0.8.
Gives us a grand total of
90,000 boxes.
That's a lot of boxes.
It's a huge go down.
It is okay. Ready for a little paper folding challenge.
Oh, I like this kind of hands-on geometry.
Example 10 and 11, use a rectangular piece of paper to create cylinders.
So we're really exploring how shape affects volume.
Exactly. In example 10, the paper has a certain width, which becomes the height of this cylinder, 14 centimeters.
Okay.
And when it's rolled up, it forms a cylinder with a radius of 20 centimeters.
So we've got radius and height.
And we just need to plug those values into our cylinder volume formula.
Pi r squared h.
22/7 times 20 squared times 14.
That gives us a volume of 17,600 cubic centimeters.
Okay, now example 11 takes the same rectangular paper, 11 centimeters by 4 centimeters.
Okay. Same starting point, different approach.
And this time they fold it along its length.
The 11 centimeter side.
To create a cylinder with a height of 4 centimeters.
So now the 11 centimeters becomes the circumference of the base.
Exactly. 2 pi r equals 11 centimeters.
And the width 4 centimeters is the height.
So first we got to figure out the radius.
Right. We need r to use the volume formula,
From 2 pi r equals 11. We get r equals 11 divided by 2 pi.
which is 7/4 centimeters.
Now we've got radius and height.
Time to calculate the volume.
Pi r squared h.
22/7 times 7/4 squared times 4.
And that gives us a volume of...
38.5 cubic centimeters.
So it's amazing how the same piece of paper
Same area,
can create cylinders with different volumes.
depending on how you roll it.
Shape matters.
It really does.
So we've covered an incredible amount of ground today.
We have.
From the areas of polygons to the surface areas and volumes of cubes, cuboids, and cylinders.
And it's all thanks to the excellent resources you provided.
And what's really cool is that these aren't just abstract mathematical formulas,
No, they have real-world applications.
like in construction design packaging.
Even simple things, like figuring out how much paint you need.
Exactly. Now here's something to ponder.
Okay, I like a good pondering.
We touched on how different arrangements of cubes can have the same volume, but different surface areas.
Like stacking them differently?
Exactly.
Yeah.
So think about this. What implications might that relationship between volume and surface area have
Okay.
in fields like packaging design?
Where you want to minimize material, but maximize what you can fit inside.
Or even in nature,
How do organisms optimize these properties?
for things like heat exchange or nutrient absorption.
Fascinating questions.
It really highlights how these geometric principles are woven into the fabric of our world.
From the buildings we live in to the products we buy.
And that brings us to the end of our deep dive.
It's been a great exploration.
Remember, the world of mathematics is vast, and there's always more to discover.
So keeps exploring.
And thanks for joining us.
It's been a pleasure.
Until next time.
See you then.